So what's up guys, this is again your resident chemistry tutor Mark, and today we will be talking about solution stoichiometry. So this is now the final leg of our series of lectures regarding AQ solutions, and now what we will be talking is about the quantitative relationships between the reactions that occur in solutions, particularly in aqueous solutions. So here we will be applying the concepts that we have learned so far in stoichiometry. In regular stoichiometry, the one that we have discussed in our previous lessons, or rather in our previous lesson, we apply it now here in reactions that occur in solution. So we will now be combining the units of concentration that we have learned into stoichiometry. Now we will also discuss another an application of solution stoichiometry, which is titration. We will also, and here we'll give special focus on normality. In using normality in titration, since this is I believe this is where normality is will be most useful. Okay, so let's start. Now, the diagram that I have shown here is akin to what do you call this? To the diagram that you usually see in the stoichiometry chapters of most textbooks. However, we have added another conversion factor here, which is the molarity, the molarity of the substance. Okay, so how does the molarity of the substance of the known substance related to in getting the mass of the unknown? So for example, we want to get the mass of substance A. So regular stoichiometry dictates us that in getting the mass of substance A, we need it converted to moles using a smaller mass, and we convert it to the moles of the substance B, which is our known substance, using their coefficients from their balanced chemical equation. However, most of substance is in solution form, so. And what we're just given is the concentration, let's say the concentration and the volume. So how do we interconvert that? May I draw your attention to the board here? Wait. Okay, that's it. Now here, we know that, wait, I think this one's not working. We know that molarity is a unit is moles of solute per liter of the solution. So we can say that molarity is equals to moles per unit volume, right? So therefore, the number of mole of the substance which is known is equals to molarity multiplied by the volume, or simply like this. Now you have to take note that you should convert your volume should be in liter, okay, before using this relationship. So let's try. Before that, we can given the number of moles and the molarity, we can also get the volume. So we just rearrange the equation, the expression for molarity, and you'll get volume is equals to number of mole of the solute divided by its molarity. This is the volume of the solution. Okay. This is different from the molar volume that we've learned in our ideal gases. Okay. So let's try applying this to a problem. So for example, number one, we want to analyze a silver nitrate solution. So you could add letter A. You could add aqueous HCl to the solution to precipitate out silver chloride. What volume of 0.150 molar HCl is needed to precipitate the silver ions from 15 ml of 15.0 ml of a 0.2 molar silver nitrate solution. Sorry. So first, what you need to do here is you need to identify the balance equation. We need to write the balance equation. So silver nitrate, which is in aqueous form, plus, I'll just move this here. Plus HCl is equal, will react to form silver chloride, which is solid, which is, as indicated, it is a precipitate, therefore it is solid and it does not dissolve in solution, plus the other product, which is nitric acid. So this is just, again, a double displacement reaction. How did I predict that occurred? So again, double displacement. Now to make the, well, you can do this if you want to. You can do this if you want to, or you cannot. But however, for in order to practice our skills in writing net ionic equation, complete and net ionic equations, we will write the complete ionic equation for this one. So since this is these components in the reaction are in aqueous form and they are ionic compounds, therefore they will dissociate into their respective ions in the solution. So silver cation plus nitrate cation, plus now remember, I did not put coefficients in the equation since they are already balanced. If you account the number of ions in the solution there, so we have AgCl, since they will not dissociate into ions, plus now we remove the spectator ions, which were in the ones whose phase who remain aqueous, who remain ions both in the reactant and the product side. So that will be the nitrate and the H+. So your net ionic equation therefore will be so that means 1 mole of silver cation will produce 1 mole, also 1 mole of silver chloride. The same goes with chloride. 1 mole of chloride will produce 1 mole of silver chloride. So what does that mean? We have a relationship between silver nitrate and silver and HCl and chloride. So that means, I'll place it here, 1 mole of silver cation is equivalent to 1 mole of silver nitrate. Similarly, 1 mole of hydrochloric acid contains 1 mole of chloride. Okay? Oh, it's not visible. I'll move it here. Oops. Would look like this, okay? Oops. Na siya. So now we use this equation, or this net ionic equation. I'll move this above. So we can use this net ionic equation to perform our stoichiometric calculations. Okay, so we have 0.2 molar. We have a 0.2 molar of silver nitrate, right? Now that 0.2 molar is can be expressed as there are 0.200 mole of silver nitrate in 1 liter of your solution. However, since our volume, the volume that we have been given is in milliliters, we can also express this as 0.200 mole of silver nitrate per 1,000 ml of your solution, because remember 1 liter is equals to 1,000 ml, so this is literally interconvertible. And similarly, in 0.150 molar of HCl, so that will also mean 150 mole of HCl per 1,000 milliliters of your HCl solution. So let's do the stoichiometric calculations for this one. I'll use another board. I hope it's visible. Wait. Oh no. Oops. Okay. So we have so we're given 15 ml 15.0 ml of your silver nitrate solution. Thus, we need to get based on the diagram that I have shown, since we're given the volume of the solution containing the substance B, which is in this case silver nitrate, we need to use the molarity of the solution, which is 0.2 molar, to convert it to moles, okay, based on our stoichiometric equation. So therefore, you use the molarity of silver nitrate, which is 0.200 mole silver nitrate over 1,000 ml, and then we convert this from mole silver nitrate to to moles of our unknown, which is hydrochloric acid. So based on the stoichiometric equation, so 1 mole of HCl is equals to 1 mole silver nitrate, right? So then finally, using the molarity of hydrochloric acid, we get the volume of the hydrochloric acid solution that we're going to need. So since volume is equals to molarity divided by the molar number of moles divided by the molarity, so we use the molarity as a conversion factor. So for every 0.15 for every 150 mole of HCl, that is equivalent to 1,000 ml of that HCl solution, right? Based on our concept of molarity. So we cancel our values, cancel. So this is our unknown, so that should be the one that will be retained after canceling all of our values. So this will also be cancelled, since they are 1,000 is the value 1,000 is both in the numerator and denominator. Therefore, our answer will be 20.0 ml of your HCl solution, which of or rather 20 ml of 0.150 molar HCl solution. Okay, so that will be your answer. So let's try another example. A sample of 7.75 grams of magnesium hydroxide is added to 25.0 ml of 0.2 molar silver nitrate. How much of the reactants and the salt product is present after the reaction? So before we need to know the amount of the products formed in the reaction, we need to know first how much of the reactant will be present after the reaction. In this case, that means So here in this case, that means one of either magnesium hydroxide or the nitric acid will be fully consumed in the reaction. So that means we need to know first which of the two will be our limiting reagents. So we apply our concepts in getting our limiting reagents. Let's say I want to start with nitric acid. I want to know how much magnesium hydroxide does it need to consume this amount of nitric acid. But before that, we need to establish our chemical equation first. So magnesium hydroxide plus nitric acid. This is aqueous and aqueous. We have an acid and a base, so we expect that the reaction will be neutralization reaction. So it will be neutralization reaction or acid-base reaction will form. I forgot to turn on my web. There. So neutralization reaction will result to for the formation of salt, which is magnesium nitrate and water. So it's just again double displacement. This will combine and this will combine to give you this product. Okay. Now, since we have established our reaction, we need to balance this. So obviously they are not balanced. So reactants and products. So we try again the ion approach. The ion approach for balancing reaction, for balancing the double displacement reaction. So magnesium hydroxide, H plus, and nitrate. So in the reactant side, we have one magnesium ion. We have two, since the subscript is 2 for hydroxide. We have one H plus and one nitrate. For magnesium, it's still 1. Now, since OH and H here is combined, this can be expressed. So, this can be expressed as HOH. Okay. Now, this HOH. Now, the H came from our nitric acid, and this one came from magnesium hydroxide. Oops, something is about none. Okay, so going back, so we have for water here we have one OH and one H plus, and for the nitrate in magnesium nitrate we have 2. So what we do, what I did first is I multiplied nitrate by 2. So since it is attached to the H plus in our equation, so this will also be multiplied by 2. So 2, check, okay? Now in the product side, the OH is not balanced. So we multiply this by 2. At the same time, your H plus, since in the product side your OH is attached to the H plus, it will be also multiplied by 2. So that will be equal to 2. Wait lang. So that will also be equal to 2, and this will also be equal to 2. So now they are balanced. So balance, 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 balance. So they're balanced to begin with. Therefore, our balance reaction will be this. We have 2 here, and this is also multiplied by 2. Wait lang. So that will be our balance reaction. So now we use the we use this balance reaction. We use the given quantities to determine the limiting reagent. So I'll start, as I've said, I'll start with the 25 ml of 0.2 molar of nitric acid. So like we did previously, we have 25 ml of 0.200 molar of nitric acid, which is 200 mole of nitric acid per 1000 ml of it. Then now multiplying this will give you the mole of nitric acid. So based on their balance coefficients in the chemical equation, we need to we can convert this mole nitric acid to moles of magnesium hydroxide. So 1 mole of magnesium hydroxide. So this will now be in brackets. It's equals to 2 mole of nitric acid. Then since the given for the magnesium hydroxide is in grams, so we convert this into grams using its molar mass. So the molar mass of magnesium hydroxide is 58.32 grams of magnesium hydroxide per 1 mole of magnesium hydroxide. So cancel all the necessary units, and what you get is 0.2916. 0.2916 grams of magnesium hydroxide. Now this 0.2916 is much smaller than the given 7.75 grams of magnesium hydroxide. Therefore, our limiting reagent in this reaction is our nitric acid. Okay, so this is our limiting reagent. So now, since we already know what is our limiting reagent, we can now determine the amount of products, the amount of reactants and products left after the reaction. So after the reaction, so obviously since our nitric acid is the limiting reagent, therefore there will be 0 mole of it left. Okay. Now for the magnesium hydroxide, since our limiting reagent is nitric acid, obviously magnesium hydroxide will be our excess reagent. So how do we get the amount of magnesium hydroxide left in our reaction? So we are given 7.75. Is it 7.75? Yeah. We're given 7.75 grams of your magnesium hydroxide initially. Now, we have calculated that 25 ml of your 0.2 molar nitric acid, as we have shown earlier, will consume 0.2916 grams of your magnesium hydroxide. So we subtract this value of magnesium hydroxide to the initial value, to the initial value of magnesium hydroxide in our problem, minus 0.2916, and what you'll get is 7.458 grams of your magnesium hydroxide, that is left after the reaction. Now, how about for the product na water? So again, we use our limiting reagent as our starting material for our stoichiometric calculations in determining the amount of product formed, since it is the one that is fully consumed in the reaction. So again, since molarity is since moles is molarity times volume in liters, so we use that again, 25 ml multiplied by the molarity which of nitric acid which is 0.200 mole per 1000 ml, multiplied by then we convert this to mole water using their coefficients in the balance equation. So 2 mole water per 2 mole of nitric acid. So for the guidance of everyone, again, here is our balance equation. Wherein the coefficient of nitric acid is 2 and the coefficient of water is also 2. Therefore, 2 moles of water is equals to 2 moles of nitric acid. Then convert this to grams using the molar mass of water. So 18.016 grams water per 1 mole of water. So this is equal to how much is that? 0.0908 grams of water. Okay. Now for nitric acid, why is this misaligned? Oh my god, wait lang. Oops, hey, stop shaking. Now for nitric acid, we do the same, not nitric acid rather, for magnesium nitrate, so it will be, again, we do the same thing as what we did to water. So for 1 mole of magnesium nitrate, as shown in our balance equation, we have 2 moles of nitric acid. Then we convert this to grams using its molar mass. Using its molar mass nga 148.325 divided by 1 mole. Okay, so therefore the number of grams of magnesium hydroxide is 0.3708 grams. Okay, So that is the total number of mole. That is those are the amounts of the reactants and products present in our reaction. Okay. In our reaction after the reaction. So what's up, guys? I'm back again. So we will be doing. So today we will be talking about titration. So what is our titration? Titration is actually a process of determining the amount of a known or the amount of a pure substance, may it be an element or a compound, in a material, which is here we call the sample, by allowing it to react with a solution of known concentration of another reactant. So that unknown is what we call that unknown amount of your that unknown pure substance, maybe it be an element or a compound whose amount you do not know, is what we call the analytes, and that solution of known concentration wherein you're allowed to react the analyte with is our standard solution or titrant. Okay, so despite the numerous modern methods or modern techniques of quantifying the amount of analyte in a sample, it is still one of the most commonly used methods of determining the analytes. So, oops. Now the equivalence point. Now in the titration, this is what we call. There is a point on our titration. That's what we call an equivalence point. Now the equivalence point is actually theoretical. It's very, very difficult, if not impossible, to determine the actual equivalence point of a sample of a titration. It's a theoretical point in the titration in which all of the analyte has already been reacted, or all of the substance in the sample of the unknown substance in the sample has already been reacted with the solute of the standard solution that was added into the sample or into the material. Now, at this point, no reactant or product is no reactant remains in the reaction vessel or in the solution wherein the standard solution or the analyte has been added into. Only the products have the what we call this remains. Okay, so how do we know if the equivalence point has been reached? So we add indicators in our reaction solution because it indicates when the equivalence point has reached. So it usually indicates by using usually through a color change. So for example, in this titration of an acid with a base, so we have 20 ml of acid added to a flask. Then we add 2 drops of our indicator, which is in this case phenolphthalein, which is phenolphthalein. Then the standard base solution, which is sodium hydroxide, whose concentration is already known, is added into the solution. Is added into the unknown solution. Then this is standard solution is slowly added until the indicator changes color. Now, the phenolphthalein, when the amount of acid is greater than the base, its color is it does not exhibit any color, thus colorless. Now, if the amount of base is greater than the amount of acid, or rather, only the base remains in the solution, that is, tanan mga acid nag-react na, the color of the color of the solution turns from colorless to magenta. Okay. Now the color of the phenolphthalein when an endpoint or when an equivalence point is reached is not the hot pink or the magenta color, but a very, very light pink color. So what you see here in the illustration here, actually, that is not already the equivalence point. That means too much base has already been added. Okay, so we'll try to apply normality in our titrations. So we know that. So remember that at equivalence point, or rather in titrations, the equivalence of the reactant or the analyte, let's say, let's try this unknown. The equivalence of the unknown reacts with an equivalence of the titrant or the standard solution or the reagent. Okay. Now at Now at equivalence point, the equivalence of the unknown present in the solution, let's name this total, is also equal to the equivalence of the titrant that was added in the reaction solution. Okay, now we know that normality is expressed in equivalents per liter, right? So we can also say, just like in molarity, normality is equals to equivalence per unit volume. So remember that your volume should be in liter. Therefore, equivalence is equals to normality multiplied by volume. So substituting this expression to here, therefore, wait, I'm running out of whiteboard space. So therefore, NV of your unknown is equals to your NV of your titrant. Okay, let's try applying this to some of our examples. So let's say for number 1. Oops. What is the normality of the sulfuric acid solution when 34.3 ml of it completely reacted with 2,345 grams of sodium hydroxide? So the beauty of it here is that we do not need to write the valence chemical reaction for this one. Okay, that's the beauty of normality. You don't need to know. You don't need a balanced chemical reaction in order to determine the concentration, the amount of one substance to the other. So here we try number 1. Okay, wait lang. So let's try number 1. So sorry. Anyway. So we have 34.3 ml of H2SO4 solution. And what we're given is 0.2345 grams of sodium hydroxide. Now, since we need to know the concentration of sulfuric acid that allowed to react, so therefore, that means at that point, equivalence of sodium hydroxide is equals to the equivalence of sulfuric acid. So since this one, the equivalence here is NV, that is pretty straightforward. And this one here, we do not know what is the equivalence here, since we're not given the normality nor the volume of sodium hydroxide. What we're just given is grams, okay? Now remember, in the expression of your equivalence is equals to the number of moles multiplied by alpha, which is our number of reacting species, right? Number of reacting species. Now for sodium hydroxide, the number of reacting species, since it only has one OH, that means their alpha is equals to 1 for sodium hydroxide. Okay? So the number of moles can be obtained by converting this to moles. Okay? So therefore, the equivalence of NaOH will therefore be 0.2345 grams of your sodium hydroxide. Convert this to moles, so 1 mole of sodium hydroxide is equals to number of moles of sodium hydroxide. Is equals to it equals to 39.998 grams of your sodium hydroxide. Then multiply this equivalent. So remember that the unit for alpha is equivalence per mole. So 1 equivalent of sodium hydroxide is equals to 1 mole of your sodium hydroxide, which is equals to okay. So we'll not answer that now. So we have obtained this expression, right? We substitute this to this one here. Now for the equivalence of sulfuric acid, we're already given the volume. However, we are not given the normality. Amo pa nang ginapangita ta. So since ang volume sa sulfuric acid is in ml, so we need to it's 34.3. Yeah. So we need to it's 34.3. So we need to convert this first to liter, since normality is equivalent to per liter. So this is equals to 0.0343 liter. So we already have the equivalence of sodium hydroxide, and we know that the equivalence of sulfuric acid is N it's like this. So therefore, the normality of sulfuric acid is equals to the equivalence of sodium hydroxide divided by the volume of sulfuric acid in liter. Okay, so if you want, if you're comfortable, you can also not convert this volume to liter. How you can retain its milliliter value. However, That means you need to convert the 0.2345 grams of sodium hydroxide to milligrams, okay? Because equivalence per liter is also equal to milliequivalence per ml. So whichever you're comfortable with. So as the saying goes, just pick your poison. So therefore, this is equal to, I need another whiteboard space, forgive me. So this is equals to 0.2345 grams of your sodium hydroxide multiplied by one equivalence per 1 mole all over 0.0343 liters. So, and the final answer will be 0.1709 normal of sulfuric acid solution. That's it, okay? So we'll proceed to the next problem. A 35 ml sample of 1 molar of potassium bromide is allowed to, and a 60 ml sample of 6.6 molar potassium bromide are mixed together and allowed to and evaporated until the final volume is 50 ml. So we need to know how many grams of silver nitrate is required to precipitate out the silver bromide in our final solution. So since we're given molarity, we need to establish again the chemical reaction for that one. Okay, so why is it so hard to erase? So wait. So we have let's try making a flowchart out of it first. So we have 30 ml. If correct me if I'm wrong. Sorry, we have 35 ml of our 1 molar or 1.0 molar. Oh, is it not visible? So we have 35 ml of 1.0 molar potassium bromide plus 60 ml of 0.6 molar potassium bromide, right? So this was combined together and allowed to evaporate to 50 ml. Okay, so what does that mean? That means the 50 ml solution of KBr will have a new molar concentration. Okay, so how do we know the molar concentration of this one? Since we already reduced the volume, we did not change the number of moles of KBr. So that means that the number of moles of KBr in this 50 ml of our solution is the total number of moles of the KBr here. So therefore, the molar mass of our KBr, the molarity of our KBr is equals to the number of moles of these two combined KBr solutions divided by its volume, which is 50 ml or 0.05 liters. So we need to know the total number of moles. Again, we employ the relationship between molarity, which is, and the number of moles, wherein number of moles is equals to molarity times volume. So we employ that method here. So the total number of moles therefore is equals to one molar of your potassium bromide solution multiplied by its volume, which is 35 ml, are converted to liters. It is 0.035 liters plus the molarity of your 0.6 molar KBr solution multiplied by its volume at 0.06 liters. We substitute that to our NT, to our total number of moles here, and what you'll get is, I'm running out of whiteboard space again. And what you'll get is divided by 0.05. Now the final concentration will be the final concentration will be 0.035 plus 0.06 times 0.6 will be 0. Or rather, wait lang. Or rather, I forgot. We don't. Sige na lang. Ito lang concentration divided by 2. Divided by 0.05. Is equals to 1.42 moles per liter na KBr solution. Okay. Now, however, since this solution of KBr is already this solution of this amount of KBr solution, which is 0.5 liters, is allowed to completely react with silver nitrate. Yeah, with silver nitrate. Therefore, we don't need actually to know the concentration of potassium bromide, but we only need to know that the total number of moles of potassium bromide here. So solving for this one, this is equals to 0.071 mole of your potassium bromide. Now this is the amount of potassium bromide in our 1.42 mole per liter KBr solution that will react with silver nitrate. Okay, so we need to know how many grams of silver nitrate will react here in this number of moles. So therefore, from 0.071 mole potassium bromide, we calculate for the moles of silver nitrate based on our balance equation. So 1 mole over 1 mole. If you going back to our balance equation earlier, there was what do you call this? Oh, I did not write the balance equation. I'm so sorry about that. Okay. So we established first our balance equation. So silver nitrate plus potassium bromide is equals to, so this is again double displacement, and since it is said that it will precipitate out a silver bromide, so the silver bromide is solid plus potassium nitrate. So similar to the reaction of hydrochloric potassium chloride with silver nitrate, the ratio here is just 1:1 ratio. So going back, we already have the total number of moles of potassium bromide. So we convert this to mole silver nitrate using the the balance equation, as you can see here, is already balanced. So convert this to grams, so which is 169.88 grams silver nitrate over 1 mole silver nitrate. And what you get is, cancel out all the units, and what you get is 12.06 grams of your silver nitrate. Okay? So that will be your answer. So again, this is the end of our final leg of what do you call this? Of our series of videos regarding solution stoichiometry. I hope again you learn a lot from it. So my apologies for any technical difficulties that you have noticed in this video. So so again. You cannot actually solve this in just you cannot actually master this lesson in just one go. You really need to do more and more practice so that you can be able to solve more complex to solve more problem-solving questions, more complex than what I have solved here in our examples. Okay, so bye bye.